In practice sheet 15.6, we're going to be talking about making and testing generalizations. Let's talk a little bit about what we mean by the idea of making a generalization. Remember, the best way to learn from a video is to take notes. Whenever I'm writing, you should be copying down the concepts that I'm explaining and drawing pictures and diagrams to go with your writing. Okay, so in math class, when we make a generalization, we're going to follow these 3 steps. Step 1, we're going to look at some specific examples of shapes that have certain attributes. Remember that in 5th grade math, the shapes that we're looking at are typically what we call plane figures, which means they're just flat shapes. We haven't gotten to 3-dimensional shapes quite yet. Step 2, after you've looked carefully at the attributes of these shapes, see if you can notice a pattern or something that all of the shapes seem to have in common. Here's the 3rd step for making a generalization. Make a statement about the pattern that you think is always going to be true, even of other examples not shown in your set of shapes. Okay, so let's look at an example of how this would work with question number 1. Question number 1 asks you to consider this generalization. All triangles have right angles. So step 1 is to look at specific examples of shapes that may have this attribute of a right angle. And I'm just going to draw this freehand, so forgive me if they're not perfect, but here's a triangle that has a right angle. Do you agree with the generalization that all triangles have right angles? I can draw a 3-sided polygon like so, and I can see 3 acute angles, and I can draw a 3-sided polygon that has 1 obtuse angle and 2 acute angles. So in this case, we're going to, after looking at these shapes that have these attributes, notice the pattern that not all triangles have to have a right angle. Now we're going to make a statement about this pattern. So we can say that although all triangles must have 3 straight sides, not all triangles must have right angles. That is a true generalization based on the shapes that I've drawn below. Okay, now let's look at question 2. All rectangles have right angles. Do you think it would be possible to draw a rectangle that doesn't have 4 right angles? And the answer is, of course, no. We can't draw a rectangle that has an acute or an obtuse angle. So in this case, we're going to agree with this generalization, and we don't have to do anything further with question 2. For question 3, let's consider this generalization. Any 2 triangles can be joined to make a rhombus. I know that if we join 2 isosceles triangles together, or 2 triangles with 2 equal sides, then we will make a rhombus. So if we look here, we've got 2 isosceles triangles joined together at their 3rd unequal side, which is here. And I can see that when I place those together, I've made a rhombus. So there's my rhombus. Let's think about if we can introduce other examples to our set of shapes that would prove that this is not a true generalization. So consider for a second if we have 2 scalene triangles. If we join 2 triangles together with all of their sides not being equal, that's what a scalene triangle is, will we end up with a rhombus? So here is one scalene triangle, and here is, oh, 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 Okay, so here I have two scalene triangles, and you can see that when I place them together and kind of rotate them a bit, like so, I do not end up with a rhombus. So this shape, even if I kind of even it out, that's clearly not a rhombus. That's just a larger triangle. Okay, so now we need to revise this generalization to say any two isosceles triangles can be joined together to make a rhombus. Remember that in the directions they asked us to provide an example that would prove that this is not a true statement the way it is. So you can also provide this example here of joining two scalene triangles together. Let's consider this generalization. All rectangles can be cut in half vertically or horizontally to make two smaller rectangles that are the same size and same shape. Okay, so if you cut something in half vertically, that means you're going to draw a line that goes up and down to cut it in half. If you cut something in half horizontally, you're going to draw a side-to-side line. So if you take this generalization that all rectangles can be cut in half, let's see here. All rectangles can be cut in half either vertically, which would look like this, or horizontally, which would look like this. Okay, all rectangles can be cut in half vertically or horizontally to make two smaller rectangles that are the same size and same shape. So let's look at these that we've created. Do we have two smaller rectangles here and here that are the same size and same shape? Yes, we do. Even though we've created two small squares here, it looks like we have 4 equal sides, we know that squares are a type of rectangle. So that is true in this case. Let's look at our example here. This rectangle that I created appears to be the same as this one. So it looks like so far our generalization is true. Let's see if we can come up with another example of a different rectangle and just see. Let's see, if we cut it in half either horizontally from side to side. Okay, that made 2 equal rectangles, that makes sense. Or vertically up and down. Yes. So I would agree with this statement. Okay, this one is a nice easy one. Intersecting lines are also parallel. We know that this is not true because intersecting lines are lines that cross each other. So I could draw an example of, let's see, in this rectangle, this line intersects with this line at this point. Let's consider the definition of parallel lines. Parallel lines are those that are always the same distance apart and never cross. So it's impossible to draw a pair of lines that both intersect and are parallel. Okay, I'm going to let you work on question 6 and question 7 on your own. Let me know if you have any questions.